Really excited to interview Cheng, Principal Research Scientist at Autodesk AI and Research Manager. I have been following Chingyi's work for a while and the amazing research Autodesk AI is doing. Like, I'm very inspired and couldn't be more excited for this interview because, like, first fact, Chingyi's background is mechanical engineering and architect, and he transitioned into AI as a researcher. So that's itself is like very inspiring to know people from AEC having this kind of journeys. And second is like a lot of cool work he has been research with the team. So just to know that journey and insight is gonna be very interesting. Thank you, Chingy, for your time to do this.
Thank you, Mayor, for the introduction. I'm also very excited to be here to share some of the experience and work we have been working on. Also, as you said, all these works are not done by myself. It's a collaboration with many people from different disciplinary and different companies and different schools. So yeah, I mean, all credit to him to them, and yeah, that's get started today.
Yeah. So before we move on to your journey part, like, can you tell us what is one point of time where you got very excited about AI and you had to make the switch from engineering architecture to AI? What was that realization moment?
It's not actually a exciting moment. It's actually a continuous search process. So maybe I can explain it through some of these slides. So it's actually as you know, I'm not starting as an architect. I'm also not starting as an AI researcher. So it's like there's a serious transition that changed my thoughts to do this and to do that, and in the end I'm doing what I'm doing now. So I'm probably gonna spend maybe 3 to 5 minutes. I can show how I transit from this role to that role to and until today. Yeah, if that's okay. Yeah.
Yeah. So without much ado, let's dive deep into your journey. Can you share us how you started?
Yeah, great. Yeah, I started my study in mechanical engineering in undergrad, but I thought I can do design such as airplane, car design, or industrial design in mechanical engineering major. But at that time, the course structure or the direction doesn't really fit my desire. I really want to find an area that my creative thinking and engineering thinking can keep fighting with each other, and I really enjoy that kind of process. But purely doing mechanical engineering, couldn't fulfill that kind of desire in my mind. So I decided to transit to architectural design school, and I feel architectural design is actually exactly that kind of thing you will be doing every day. You're always thinking about this two confliction with yourself and even with others. So yeah, that's why I switched. But right after I switched, I found you know something this is not really working well at that time. So traditional architectural workflows or tools, they're kind of slow for iteration and also hard to create complex design and modify it, right? So if we talk about just doing hand sketch, physical modeling, and CAD drawing, and all these kind of traditional things. So yeah, that and then I also have been trained as an engineer, so I know lots of coding, or even in mechanical engineering there has been people have been using very advanced parametric modeling tools such as CATIA, and also using script to do design as already. So I started to think, how can I utilize those programming tools or more advanced modeling tools to help me. So I started to do lots of parametric design, computational design, like all many others have been doing, including some of the pavilions, or even my undergrad thesis, which is more like a bottom-up agent-based city renewal system, like you handcraft a SimCity game, right? So pretty much like that. But at that time, I really truly believed that computational design is going to disrupt the design industries. Everyone should learn how to learn coding. I was really naively believing that about 10 to 12 years ago. So at that time, I really tried to utilize computational design to do my own design and also teach others, right? So but at some point I realized that the adaptation rate or the speed of adaptation is not really as fast as I'm expecting. Still, till even today, it's only a small portion of people who are able to utilize computational tool in their daily life for architectural design. So there are many potential reasons we can discuss, but two of them I think is one kind of important is technical barriers. So one is technical barriers. The technical barrier is not saying like, oh, okay, no one can learn Grasshopper Dynamo, but it's more about when you dive deeper, there's just too wide for everyone to cover everything, right? So even just for simulation optimization, it's already really, really going to be very deep. So you cannot expect everyone can utilize or understand everything and code everything, and also everyone has a spectrum of how much they can accept this, right? So really, it's not going to work in this way for every designer. And also, one more important thing is this kind of programming tool or even visual programming tools still are not really intuitive enough for you to feel or interact with the design, right? Although you can see the visualization by tweaking the slider, but it's still not the way we really want to express the thoughts, right? So this or it's a different way to express the thoughts, right? So this is just different mindsets. So everyone has to be able to adjust in between those mindsets. So it's really not going to work for everybody. So so at that time I started my grad school at MIT. So I really start to think, what is the solution? What will be the solution? Or potentially, how can I do? So I was thinking more like, instead of asking everybody to learn coding or dive very deep, can we provide more interactive ways that everyone can utilize the power of computation while still require low or no code, right? So but how can we do that, right? So at that time I found, at MIT, it was 2014, everyone was talking about machine learning and AI. That was just around about the time, right? So the boom just started, and then AlphaGo and all the things just keep happening every day. So I started to think, okay, how much should I know? And also, how can that be helpful to create this kind of imaginary schema or ideal schema I'm looking for? So at that time I started to take many classes at MIT, and also I work as a research assistant at MIT Media Lab, the Tangible Media Group. So in Tangible Media Group, I participated many of their research projects. Basically all of them are more in the HCI field. But it's not traditional UI, user experience HCI, but more about interactive material, programmable material, and this new type of interfaces. So I work on those projects not because I'm really into that direction, but because I want to use those projects as a playground to try how all these new ideas or new skills I have learned, right? So for example, this is a project we did with Tangible Media Group people. So this is a, okay, I can actually play video. So this is a sports garment that can open and close on the back. So there are many flaps that can open and close in the back. So when you are basically jogging or dancing, the back is hot and humid and you are sweating a lot, those flaps will open. And then when you cool down, feel cold, these flaps will close. So, but the problem is the fashion designers we work with doesn't have this expertise of, knowing how these flaps will open and close. And also this is a new type of material which is driven by bacteria, not electricity. So this is really hard to also simulate it. So it takes a lot of time to do finite element analysis. So this is not going to work if we want to design if we want to design an interactive material without an interactive tool, right? So the tool has to be real time and interactive. So at this time, I try to use some data driven method that try to boost the simulation into a real time a speed, such that whenever the designer draw a curve or draw some flaps, you will immediately see how it moves up and down. And so basically the idea is pretty simple. You just pre-compute many flaps ahead and different shape, different situations. And whenever you have a new shape, you try to find the nearest neighbor. And then you use that pre-computed result as some kind of approximation or initial starting point. And then after that, you keep running the simulation. And then instead of starting from the scratch, you jump to a very close state, and then you keep doing that, and that will bring you a very large jump, reducing the amount of iteration required to a very minimum numbers. So you can actually achieve real time. So I actually utilized similar idea in some of our later papers, but again, this is just some of the projects I utilize as a playground so that I can try all these kind of new ideas. And this is another project we do, pasta design, shape-changing pasta. So you can actually design your own pasta shape. So design your own pasta shape by tweaking the parameters, and you can draw some patterns, and then you basically can see once you cook it how the pasta will look like. So this is using similar idea by basically pre-computing and do data-driven. So it's not fancy machine learning yet, but it's just some initial ideas I want to see if this can really help the design process, right? So when people can interact with this interface, I mean, we collaborate with a chef in Boston, and then he actually designed many dishes using our shape-changing pasta. So yeah, and then the previous project was the fashion designers, right? None of them are really computational designer or have this kind of ability to code or simulate things, but with this kind of tools, they are able to do that, right? So that's probably the second part of the journey. And then
I
the
have
third
two
part.
questions.
Sure. Feel free. Yeah.
For example, like even like I did bachelor's in engineering, and for master's in US, like it's a 3-year program in States. So first is like you said you did machine learning courses at your time at MIT. So
Yeah.
was it like part of the curriculum, or you were exploring other schools, and how are other batchmates at that time? Like what was the atmosphere?
Got it. So the program, the first, I did 2 masters at MIT. So the first program I joined is basically the computational design masters in architecture major. So this is called a program called SMARCS in computation. So the program itself is super flexible. It's a research oriented program. So you don't really have many required courses, but you are basically allowed to freely take courses at MIT and find a research topic, and that will become your thesis. As long as this is related to computational design, that will be actually okay. So actually, all of my classmates are working on or basically exploring different directions. Some of them are doing VR, some of them are doing robotics, and everyone is having their own direction. So, and mine is more like this kind of interactive design tool plus AI related applications. So yeah, that was the first program gave me this flexibility. And then after that, I applied the second program at under the MIT C-Cell AI Lab computer science degree. So basically, how it works at MIT is you basically need to find a professor that can support or willing to supervise you, and you have to also fulfill a bunch of course requirements, and then you submit this to the committee, and then if they say yeah, this is okay, and then you will be able to do a second degree. So yeah, that's how I did that. So it's not I mean, if the first program were not flexible, I wouldn't be able to do this. Yeah.
I see. That's super interesting. And like uh, we hear a lot about MIT Media Lab and the amazing work they are doing. So how is it? Is it like working there? What are the different areas and explorations people are doing, and like how did you get into that space?
Yeah, so yeah, really, there are three things or three places I have been playing around at MIT. One is the computational design group. Secondly, is the computer science department, and third is of course Media Lab, the Tangible Media Group (TMG). So I joined their research project actually even before my first semester at the MIT started. So I randomly found that they are looking for some collaborator for a summer project, and then they are looking for some kind of computational designer or person who can do geometry modeling and simulation and something like that. And I found, okay, since I'm actually joining MIT, and I can just arrive a little bit earlier to the States, and then join their research project, and then yeah, and then they say, oh yeah, actually, why not? This is a good fit, and so that's how I get started. But after that, I just keep working with them, and even officially became a research assistant in the group, and contributed to some of their projects. And yeah, I think that's how I get involved. Yeah. But
That's
this is
great.
not like a unique situation. Everybody at MIT, especially in our program, many people are just reaching out to different department, different labs at MIT, and then have some collaboration, even work with them. So this dynamic is not very unique. So I'm just one of those people who did this. Yeah.
Got it.
Yeah. Should I
Yeah,
continue?
yes, yeah, for sure.
Okay.
Yeah.
Yeah. So after MIT, eventually I really think there are three pillars I really like, which is the machine learning, design, and how machine learning can work with designer, which is the interaction part. So as you can see on the bottom right, so these three circles, the intersection of these three circles is the place what I really interested in. So I decided to join Autodesk Research, and then they are really. I was really lucky because at that time they just started to think about why not we can explore AI for designers for Autodesk products, right? So I joined them and started to think about what we can do. But at the beginning, what I was thinking is more like how we can apply the existing algorithms or technology to some of the problems or some of the desired interactions I'm hoping to achieve, right? But the problem is, it's not going to work for many situations. First of all, the representations are not actually, we use in architectural design or any kind of design. It's not images or point clouds or even voxels, right? So
Mhm.
we really need a different representation, or at least find a way to represent it, or make it more usable for the designers, right? And you know that's the biggest problem. And also those problems, trendy machine learning problems, and then people are tailoring their models for solving those problems, and then that's why it doesn't have this kind of uh, how to say that, customization, or a little bit more trick that is more suitable for solving our problem, right? So even if you can solve even if, for example, a graph neural network is pretty generic, that can be solving all different kind of things, but how can you tailor it to solve your own problem requires a lot of research, right? So right after probably the first project I did at Autodesk, I found that, okay, this is not gonna, work in this way. So I have to
Mhm.
dive into the algorithm myself, to actually develop the solution we really need, or to explore the solution, and more importantly, to advocate the the problem to the AI research field, right? So
Mhm.
basically, if nobody in the AI research field really care about any AEC related problem, and if only me or our team at Autodesk is doing this is not going to be growing in scale, right? So
Mhm.
the
Yep.
most important thing in AI research is that people share about research result, people care about the same problem, and whenever there's a new interesting topic, lots of people will actually contribute, and you will see like hundreds of paper on those topics every year.
Mhm.
So that's how it works, right? So for us to solve really the problems we care, it's not like we want to claim, yeah, we were the person who did this, and nobody should touch our territory. No, it's not like that. We should actually be open. We should
Correct.
advocate. This is fun. This is cool, and everyone should join. So two of the reasons I started to do AI research is basically not only just solving the problem we need by ourselves, but also advocating and even recruiting, and reaching out to people in academia to let them understand this is fun, this is worth to explore. So yeah, that's actually the things I have been doing in the past 4 years. Yeah, I hope this is a quick summary and a story, yeah, of my journey.
That's amazing. I totally haven't thought about that because, like, in order to push it to the state of the art, you need to get the AI community excited about the problem in AC, and that
Yeah,
makes a lot of
yeah,
sense. Yeah.
yeah, yeah, and of course, like, it's bi-directional, right? So you also need to get the people in the AEC field being excited for it, and then but something we haven't really resolved till even today is to have more generic or large scale data set that is available for everybody, right? So this is something we still don't have till today. So people thought like Autodesk has a lot of data, but actually not. We cannot copy or steal customers' design file, right? So it's not. So we really need to join the force together, try to find a way to come up with a large enough data set, that everybody can use and everybody can do research on those data. So yeah, that's some of the things I really want to do in the near future. Yeah.
Yeah, and I got very happy when I got to know, like in CVPR there was the first workshop where there was like point cloud BIM data, and I
Yeah.
thought, okay, we have a good start, and like things are getting better and people are getting excited about point cloud and BIM issues. So.
Yeah. Yeah, that was a cool workshop, but the data they are providing are still not really large enough, right? So if if you play with the data, you will know. So really it's just a starting point, but it's important starting point, right? So how
Mhm,
can we eventually get a larger and larger data set, and more and more people are interested in this direction. So yeah, scan to being definitely is important, and also all this kind of design related topic is important. Simulation, all these kind of things are all important. So we can name like 100 of cool topics in this industry, but it's more important is like how can we have data set and also attract people. So yeah, what we have been doing is like we do the work and publish and try to also release the data if we can. So but really it's still just starting right now. So yeah.
mhm,
um yeah, so next I think there are some of the high level thoughts about how we approach this AI for design. And then there will be several projects we can dive into. But, I also want to know, how you want to go about this next. Yeah.
Yeah, like I think like we can do like high level summary and like architecture of the model, and then we could go deeper. Yep.
Yeah. So I think basically the highest guideline for all of us at Autodesk Research is basically, especially for people who want to work on design, is we want to be more involved in and interactive. We don't want the algorithm just popping the design options for you
Yeah.
to pick, right? So we want it to be more involved, engaged, and experienced. And to do so, I think we want to solve some of the high level common pain points instead of uh, trying to say like AI is actually very creative, AI is like having cool ideas. Although maybe in some cases that's true, but what I really believe is that still I want the human designers to be able to drive their thoughts and express their thoughts. And then the tool we are building is only trying to help you to engage or improve the flow, right? So this common pain points: low level task, boring task, repetitive task, or difficult, expensive, or slow tasks. Those are the things we really want to help the designers. So in short, is basically design with you means actually let the designer enjoy the fun part in the design
Hmm.
process, right? So, but this is also very case by case. Different designers enjoy different things, and different problem or in different stage of the design process has different things to enjoy and different things to hate, right? So it really in the end it's more about who is the user, what is the problem, and it's not going to be a one solution for solving everything. So it really has to be dive into the flow and workflow, work with the designer, interview the users, such that they will tell you what is the right thing to do, right? So um, yeah, in high level, one framework we are trying to form is that we know the designers are using different representations uh, for their design process, but this process is not actually linear. It's always jumping around.
Mm-hmm.
And different representations has their own strength, right? So some of them are very flexible, describing high level abstract idea. Some of them are more, can create more sophisticated or detailed and accurate things. So different representation has their strengths. So we don't want to eliminate or focus on only one or two representation, but instead we want to help designers transiting or working in between those representations, right? So and also here, if you have to jump around, those repetitive, low level, difficult tasks will actually be happening in those transitions. So if we take a look from the previous diagram to this diagram, basically just look at a different aspect. So if we think about the green dot as the designer, so you are always looking at or observing one representation and then try to digest it and think about it and output to another representation or even back to the same representation. For example, you look at your own sketch and then try to think about how you draw the 3D, or you look at the requirement and think about how you draw some sketches, right? So you're always having this input, encoding and decoding process in your mind and working with the representations. So, and in reality, there are actually even many more representations we have been using in the architecture design process. So it's how we can help this process. So the idea is, how about we have a blue dot here, which is actually maybe a machine learning model, or a more technical way to say it is maybe a latent space, right?
Mm-hmm.
So in here, when we want to do some kind of transition, we can actually think about, for example, let's say I want to produce sketches or these layouts and detailed floor plans. I had to basically produce it by myself and keep redoing the work. But if there's a model that is observing my sketches and trying to converting it to different representations, that would be super useful. So this is called translation. I just have this blue dot doing this representation translation for me. And then there's another concept called generation, right? So instead of translating one output, I can translate many
Mm-hmm.
potential mapping, right? So one sketches can produce different layouts potentially, right? So we are basically using this uh, blue dot here, trying to look at what we have been doing as a designer and try to understand that and translate or generate results in different in different representations. So this is the highest level guideline for all the projects we have been doing. I mean, at least I have been doing in the past 4 years. So including house GAN, building GAN, and also some of the early works. Yeah, so that's the high level ideas, and then feel free I ask any question, or we can jump into any specific project. Yeah.
Yeah. So I was thinking for your observation and translation, like we have like different modes to do it. Like some people sketch on paper, or like we have image data flow plans. Like
Yeah.
what's the process of those translation, and are you storing it in vector, tensor, SVG format? Like, are you noting the time steps of each? Like, can you elaborate more on that?
Yeah, so it's not that detailed. So this is more like a research directions. So for example, in one of the project, you might be looking at, for example, building GAN. You might be looking at how we can drive from the by observing the constraints and goals and bubble diagrams to create volumetric design, right? So the blue dot is doing this kind of thing. And then in some of our early work, we were looking at how we can translate the rune sketches to layouts. Those are one way of doing that. So we are not saying we are building a generic AI system that can look at all the representations and try to help you. It's not that yet, right? So it may be 20 years later we will be able to do that. But right now, as I said, we need to be more specific into one specific workflow, into one specific problem, such that this interaction or this translation or generation is desired or useful for that kind of process or that portion of work in the whole workflow, right? So we're not building any generic things to solve all the problem together, but we use it as a map, right? So whenever you're thinking about the next project, what's missing, what's next, and whenever you are interacting or interviewing a user, what do they really want? How can I translate their thoughts, their feedback into some of this roadmap or mapping or framework we have right now, right? And then what is missing in terms of technical part, right? So for example, right now, if you need to look at the structured design system, and what is the right representation? What is the right neural network for that? And when you want to output the volumetric design, what is the right format for outputting volumes? What is the right architecture of doing this? Are we doing generation? Do we need to use GAN? Do we need to use other generative model? When we are doing translation, what do we need to care, right? So this is just a tool or a map that helps you to frame your problem and to think about the solution. So yeah, I hope that makes sense.
Yeah, and I must admit, I love this diagram. Like, it clearly shows like the whole spectrum of research you have done, and like amazing. So, can you uh give a like basic overview about like what are the different neural network or models you have used, like for example, GAN or like.
Yeah. So at the beginning, like in my earliest work, this is actually my first project at Autodesk. It was like 2017 summer. Um, as you can, I think you can guess what I was using here. So these are just very simple image-to-image translation networks, right? So, but at that time, basically, what we were doing is we want to produce an interface that can allow user to switch in between input representations. So instead of only doing sketches, right? So you can actually switch to manipulate the in the semantic level, right? So you want to allow the user to switch in between two representations, and that all will lead you to some detailed floor plans. So this was my first project, and then at that time I remember we only had CycleGAN, and
Mhm.
but the if you know CycleGAN is for like 1-to-1 domain translation, but
Correct.
now I have three, right? So how can I do this, multi-domain translation? Because at that time there was no papers like Muni or StarGAN yet, but later that year we had those. But that was the the time I found, state of the art is not enough, right? Because I want to do more. How can
Hmm.
I do that, right? So that's why we started to do that by ourselves. Yeah, here is the first example, and house scan. Now we talk about generation, right? So we do bubble diagram to layout, and of course keep using GANs, but right now you need to consider the graphical relationship between the runes, right? So that's why we need a graph neural network, but it's more tailored version of it. As I said, it's not generic graph neural network because we care more about the 2D relationships and the information. So we use ConvMPN developed by our collaborator Nielsen at Simon Fraser. So it's more about when you passing message between nodes and edges, you are passing this kind of two-dimensional tensor information instead of the vector, which proven to be more informational rich for this kind of tasks, right? So yeah, this is a combination of generative model GANs and also graph neural network. Yeah. So other work such as building GAN, our latest work it's kind of a continuation of HouseScan, but instead of keep using the image representation, we start to use a new representation called non-uniform voxel graph. Basically, we define something called voxel graph. It's basically we can sorry, not this slide, but this slide. So voxel graph is basically we if we look at all the commercial buildings, you will see the structure system and you will see some preferred divisions actually here, right? This, right? So if you look at all the building that being built, you can clearly find some patterns, no matter it's due to the facade panelization or due to the structure system. You always can find this kind of space partitioning as some part of the design intent. So instead of asking the model to produce or to generate like pixel, and that is going to be more zigzag and actually noisy, how can you create clean edges? And how can you really capture the thoughts of this design intent, right? So that's how we invented this voxel graph system, such that each voxel is not really uniform voxel anymore. Each voxel can be a different way you partitioning the space. A unit can be not like a cuboid, but more arbitrary. And you can also limit the design space. For example, if you have sunlight restriction, you don't have to utilize the whole space of the grid. You can chop some of them out, right? So this is limited. This is not allowed to build, right? So with the graph, you have this flexibility compared to voxels. And then and also this graph also provides you more geometrical information, right, compared to more generic graph. So it is kind of in between a graph and also a voxel representation, but kind of trying to bring the good from both sides. And sorry, go ahead.
Sorry to break. And the representation, like in the model, is it like on a like graph neural network level, or it's like using
Yeah,
PyTorch 3D and like on the 3D space?
it's graph neural network. So the idea is basically we represent the program input bubble diagram as a graph. And then our output or our design space, which is the voxel, is also represented as a graph. So the problem becomes how you can exchange information between the program graph and the output voxel graph. Saying that, so basically for each output voxel in the voxel graph, you want to find a corresponding color, right, in the program graph. For example, in this location, is this going to be an office? Is this going to be a toilet? Or is this going to be a lobby room or something like that, right? So for each location in the voxel space, we want to assign or pick a node in the program space to fill it. So basically, it becomes more like an attention, right? So you always have one voxel to look at the corresponding nodes in the same floor in the program space, right? It's not doing attention to other voxel, but instead doing attention to the
Oh.
program space, right? So that's how you build the relationship or connection between these two graphs. Otherwise, they are not in the same modality. How actually can you do message passing? You are not doing message passing. You are doing this pointer attention mechanism. So basically, you just iterate. You just do message passing in the program graph, and you do message passing in the voxel graph. But in between those message passing process, you have this attention mechanism helping you to pick a color or pick a node in this program graph, so that you can have this back and forth process between these two modality. And then, of course, you have discriminator to see, if the final voxel is okay or not. Yeah.
That's super interesting. Like I haven't read this paper, but like the way you are like passing and doing attention is super interesting. And I'm just wondering, like does the node have features of like the size, program, and and what about the features of the link in the graph?
Yeah, so we're not assigning features to the edges or type to the edges, but we do assign features. For example, in the program node, you will know the type of this room and also some desired, uh, basically program ratio, right? So we also have some desired ratio for each program and so on. So you will have some program level information in each program nodes at the beginning, and then you will also have voxel level representation information in each voxel node. For example, you will know the location coordinate of this current voxel, and you will also know the width, height, and the length of this voxel, right? So and also its type, right? So it's not assigned. If it is not assigned, it's empty. And then if you assign, it definitely has a type, right? So basically, that's how it works.
Awesome. Yeah.
Yeah, so basically the idea is instead of using any existing representation that is less um, suitable for our output, right? So instead of using a very fine grained voxel, chopping the 3D space into very dense voxel space that will require lots of high computation
Mm-hmm.
power. Instead, you try to find a better representation that can create cleaner results, but also save more time for you. So yeah, we did something at the beginning. Is basically we just using the same pixel output as house scan, basically just stacking house scan, and that didn't work really well. First of all, it is still creating this pixel level output. Secondly, the vertical communication is not as good as having this graph structure. So that's why we think this representation probably is better. And also in the future, like one might ask, okay, this is like, although this is flexible, this is still like perpendicular Manhattan grids, right?
Mm-hmm.
So how can you do, a tilted line or even curves?
Yeah.
But I mean, this is doable because this is a graph, right? So if
Yeah.
you chop the space not in perpendicularly, it doesn't matter. It doesn't matter for the graph. You can still compose the graph after chopping it randomly, right? So that's basically the potential of it. But the problem is in this project, we didn't have any data in that case, right? So we were using our synthetic data. We don't even have real building data for this project. So we use a synthetic data set. But of course, the representation itself has actually more potential than we shown in this project. Yeah.
I see. I was about to ask like what was the data labeling augmentation and was
Mhm.
it real versus synthetic? Yeah.
Yeah, it's synthetic. So we build more like lots of parametric models and try to generate like 120,000 buildings. Yeah.
Got it. So like for like I'm I want to know your thoughts for the synthetic data generation. Like
Mhm.
we need let's say architectural logic or domain expertise for the
Yeah.
configurator.
Yeah.
So how do you translate like so there are opportunities for architects to contribute and collaborate with AI researchers because they need this data set, they need help in labeling. Also they
Yeah.
might need help in like checking or validating whether it's a good generation or a bad generation.
Yeah, totally. So I forgot to mention this project building again is a collaboration with Obayashi. Obayashi is one of the largest construction company in Japan. So we collaborate with them, and then their architects are super supportive for this project. So we really enjoy working with them. They provide lots of feedbacks and also even working on many of those data generation process. So yeah, I think definitely this is it is, as I said at the beginning, it's a great way. You find the the place you can contribute, right? So if you are a designer, you don't know how to do AI modeling, but it's still okay if you are, having some interesting thoughts and you can contribute. So the process, I have to say, at the beginning is not easy, right? So you need to build the trust and build the communication. But later, when everyone is aligned, this is like super awesome. Yeah.
Awesome. And you briefly mentioned about the structural model
Yeah.
project.
Yes, I can just show that. So this is a ICML paper we published last year. So basically, the idea is architects usually doesn't have this structural design expertise. So, and even structural engineer, when they have to optimize for some, cross-section sizes for all the columns and beams, they also have to iterate a lot by themselves, right? So whenever you run a simulation and then you have to tweak the results and run it again and again. So really, how can we do structural optimization in a more better way? And also, even if you run structural optimization, you still using genetic algorithm or something like that. So you still have to wait for each iteration or each seed. You have to wait for the result for the simulation, right? So it will take a lot of time. So how can we speed up this process? And so basically, we propose two neural networks. One is the neural sizer, that is basically given a structural skeleton that is trying to guess the best optimal cross-section size for each element. And there's a second network called NeuralSync. It is simply trying to mimic or learn how the structural simulation system works. So it's just pretend it itself as a structural simulation tool, right? It's trying to produce all the deviation and loading and stress on each element. And then we will be able to measure the performance based on the output from the neural sync, right? Such that we can back propagate back to the neural sizer. So traditionally, if you in the second stage, if you don't have neural sync, if you are using the traditional simulation tool, of course you can still get the result, but you don't have gradient, right? So you have no gradient popping back to your model, and also you have to wait, right? So it's slow. So you basically, when you train neural sync, you're front loading those kind of simulation time when you are training neural sync, and then when you are doing this design optimization training neural sizer, you don't have to train it do the simulation anymore. So this produced a really nice results for structural design cross-section prediction. And then the more interesting thing is that because we are still using the same representation for as many structural simulation tool use, like this, graph representation for columns and beams. So you can still I'll use the predicted result to do further real simulation and optimization, right? So similar to, if you remember the flap close project I was doing. So when you have a better starting point, then you have much lesser iteration if you want to run a optimization or a simulation. So that's basically, some people will ask, like, okay, you use neural network to predict the structure system. If this is not safe, right? If neural network gets wrong, right? Yeah, we know that. But the point is not about using this as a final result. The two reasons: using this as initial thoughts or ideas, and secondly, you can further optimizing it with much lesser time, right? So many people who are doing surrogate modeling for using machine learning for simulation, I think one thing often missing is how you bridge the gap, right? So many people are claiming, oh, this looks awesome and this is real time and blah blah blah, but the important thing is how can we make it more reliable? So there are two ways. One way is like what we do here. You can basically use the output result to further doing optimization or fine tuning, Or there's another way is you can uh, loop the real simulation and fine tuning in the training process, right? So if you do several iteration, that is doing the fake or prediction for basically from neural network, and then you can add some real actions for simulation every several steps or something like that to guide your simulation results to make sure that it's okay, right? So all these kind of things are really interesting, and I think can be really potentially useful for many architectural design or simulation related problems.
Yeah, like Cheng, I must admit, like I was a structural designer, and you can't imagine, like, if you're doing a high rise, it's a non-linear analysis for structures. Like, the amount
Mhm.
of time you need to wait, sometimes it's like 5 minutes, 10 minutes for the
Yeah,
analysis. And
yeah,
I was thinking, like, what if currently we have like synthetic data, but you have a plugin which might be on ETAP, SAP 2000, or robot, like, and it's recording this data when people are doing synthetic simulation, and then indirectly it's sending to the cloud, and like we are making the whole database for it. And I
exactly.
think like that's gonna be quite useful where
Yeah, that's going to definitely be amazing. But the only thing is like if people are willing to do so, right? So we need to build the system or build a platform that is anonymous enough, right? So, for example, eliminating lots of confidential information, and such that people can be happy to share. Or, I mean, it's even more like people just participating this kind of random generated structure simulation using their local computer to share the load or something like that, right? So people can all contributing to those data building simulation process to a larger data set that is shareable by everybody, right? So as I said, this project we did here is also using our synthetic data set, but
Mhm,
again, the graph structure or the building structure, the representation itself is flexible, is generic. As long as we have enough data, this should be also going to work, right? So
mhm.
yeah, as you said, eventually if we can build a good data set or a platform, people can share structural simulation data, that would be super awesome. Yeah.
Yeah, and to your point of accuracy, like, it's it's very important. Like, even if I'm doing my first simulation for my building, like I give like sizing based on the few like simple calculations we
Mhm.
do, and then after the analysis, like if the structure columns fail, we do like propose a new sizing and stuff like that. It could save a lot of time by just doing like this quick analysis and do give a proper sizing to start the accurate analysis, like.
Yeah, yeah, totally. Yeah, so you want to shorten the iteration, right?
Mhm,
And you also want to get the feeling, and you also want to guarantee this result is usable. So having, I think the key, at least for us in this project, the key is make sure the representation is the same from your input and output, and also it's the same consistent with other real tools you will be using, right? So if this, let's say, if this output is point cloud or is a voxel or is an image, this is not going to be an easy work bridging it back to the real simulations tool, right? But if it is a graph, that's super easy, right? Yeah, so I think that's the key.
Yeah, and I was wondering, since it's a graph network, like all the parameters are features. So if someone wants to adopt this model and have a different optimizer by adding cost or some construction
Yeah,
feasibility parameters, they could just do retraining and adopt this model architecture to like have their own custom use case. And
totally, yeah.
And I was wondering, like, about the accuracy. I have seen few models on like mechanical engineering where they are doing car simulation, and those are also doing non-linear analysis
Mhm.
for structures. And
Mhm.
so, like, are there any inspirations from that space of product level structural analysis or stress analysis about accuracy, which we could also study?
Uh, that direction I'm not really familiar with, to be honest. So my research interest is still like in the design or related topics. So I didn't spend too much time tracking all those papers in that direction. But but I do agree those are really promising works, and there are many promising works over there. But one comment I guess is like uh, when we are doing data driven methods, there are many assumptions or representation or simplification we are basically using. So we just want to make sure the result is something we can continue use, right? One example is basically what we want to do here in this project is basically we have some kind of preset loading and code, but when we change dramatically changing the input code or loading cases, this might not going to work, but you have to retrain or pre-train the model. So really it's about if you understand the underlying rules and knowledge enough, right, before you really try to tune the model. And there are, as I said, there are many tricks in every papers that is tailored to their specific problem, right? So for example, in ours, we have some kind of structure prior that is talking about how we passing the information from top floor to the bottom floor. But in some cases or in some other application, maybe this prior is not actually relevant, right? So whenever you are trying to utilize existing model that look great, but you need to really understand underlying knowledge and engineering work and also the trick they apply, such that you can actually utilize in your case. Yeah, sorry, I took a little bit to explain it, but that's what I was trying to say. Yeah.
No, I think like that's a really important point you mentioned, and thanks a lot for like sharing that.
Yeah.
Yeah. I think we could move on to your next research.
Yeah, I think those are probably I will talk about some next steps,
Mm-hmm.
and also some existing project for the next steps. So we have been doing this kind of exploration, doing translating and generation in those representations. But there's a new representation or a implementation that I really care myself, which is 3D modeling sequence or programs. For example, Dynamo, Grasshopper, this kind of thing, or even some of the scripting you can write to generate your design. So, or even very naively, the parametric model itself, like Revit or Fusion or any other modeling tools, right? So why this is important is that, let's say if we use building GAN or if you use house GAN or even other models to generate 3D or 2D drawings, even if those are in solid modeling shape or in vector format, you are already able to edit it, for example, that's okay, but it's not going to be structured, right? So you cannot tweaking or controlling parametrically. So how can we, or in other way, like many designers, when they are not familiar with Dynamo, Grasshopper, they are not able to convert their model to those kind of thing representation and play with the parametric variations, right? So they have to build it manually. And the other direction is like when you have a parametric model and then your design variations or ideas are limited or bounded in that structure. So whenever you want to do some crazy change, you have to actually largely rewrite or eliminate your existing structure for your parametric design, right? So both ways are actually take some effort. So how can you have a agent or architectural machine learning model that can look at your representation in this domain? help you to translate it to another domain or construct other representation back to this domain, right? So this is really something important. I think it's going to be very powerful, but as well as very hard, right? So
Mm-hmm.
this is one important next step. And then secondly, of course, exploring different ways of interactions more, such as how about we now use a reinforcement learning agent? How can an interactive agent working with a human designer? And also, like, language models are now recently very popular. We are also exploring text to 3D ideas as well. But what I want to share a little bit today is the first one. So yeah, so the early work we did in this direction is a paper we published in 2018 with my undergrad intern Kevin friends. So the idea is, like, as I said, as you can see here, right? So if we ever produce the image result, it's hard to edit it. But if the network is producing this vector or sequential result, it's really easy to edit, like Illustrator, right? But the problem is when you train a model like the drawer network here, when it is basically drawing, outputting the actions and drawing on the canvas, this process is not differentiable, right? So if you don't have a differentiable renderer, at that time there
Mm-hmm.
was almost no differential renderer,
Yeah.
but right now there are many. So
Mm-hmm.
at that time, what we want to how we want to achieve resolve this problem is we train another network called Canvas that is trying to predict, basically taking any actions, trying to draw or imagine how the results will be looking like, right? So you have this image as an output that is basically trying to render all the actions you have been taken, and then you can in this way compare with your input drawing with your output drawing, such that this process is going to be differentiable to improve your drawer network. So that was the idea. So since we don't have a differentiable renderer, we build one using neural network to approximate it. So we submitted the paper to iClear 2019, but we got rejected. It was no, it's okay, that happens. But there are actually another two concurrent work which are doing very similar ideas. StrokeNet and this paper, learning to infer and X to 3D shape and programs. They're doing really, really similar things, and then their paper are really also great, much
Mm-hmm.
better well written than ours, because we kind of did a little rush. But anyway, the ideas were the same. So we will be able to basically let the model to take actions, for example, drawing the strokes, and then basically can rewrite those characters or actually draw the animate characters. And one interesting thing is, like, we can also do long strokes and short strokes. So basically, when you are scanning through the image, you can use a larger window first that will produce a larger or major strokes, and you can use a smaller window next that will produce the smaller strokes. And then at that time, we didn't have enough time to explore, let the model to learn when to use a larger window and when to use a smaller window. But this year there was a SIGGRAPH paper this year. They are actually doing that, and that looks super great. If you are interested, you can check it out. But anyway, this is also going to work in the 3D modeling thing. So imagine when we do 3D modeling, we are looking at the top view, side view, and front view, and then we are imagining the action we can take by looking at these three views. So the input of the model will be these three views, and the output will be the actions. And then whenever you produce actions, your canvas network will imagine the consequence of this action. So for example, you look at this ground truth views, and the first imagination about you put a first cuboid is like this row, the second row. And then by looking at the second row, you will imagine, okay, I want to put the second cuboid, and then this is the imagination of that. And then you can build these two cuboids. So that's basically allow the model to learn how to do this sequential output. And the next project, which is the CVPR paper this year, we did with the MIT and Brom, is basically do that in a more advanced way on solid modeling using the Fusion Gallery 360 data set. So basically, by looking at existing 3D objects, we can decompose it or chopping into small pieces and try to find the relevant pieces that can form the sketch and extrude operations, such that in the end you will have these operations being generated. You basically have the full parametric model being constructed, right? So the idea is called zone graph, which is actually, if you can correlate, it's really similar to building GAN, right? So you are observing a 3D geometry and try to extend all the surfaces and endpoint, and then trying to use this extension to chop the space. If you know, like many architectural designers and also many even conceptual artists, when they are trying to draw something cool, they draw those cuboids and trying to divide it or chop it gradually
Hmm.
and finally form a very complex shape, right? And this is exactly thinking about that. So by looking at the final shape of a complex object, we can try to imagine what are the potential operation or components that will help us to model it, right? So if I ask you to model this mouse, what you will do is exactly doing that, right? So observing it and see where are the potential extrusion, what are important surfaces, and so on. So yeah, we try to allow the model to learn this process by basically chopping it, and finally we will be able to construct a parametric model. So this is basically one of also the important direction we will be looking at, is basically how we can convert, instead of generate instead of 3D objects, but how about we create sequence of actions, or creating even a program to describe it. That would be more useful for designers. Yeah, I think that's probably all the projects I want to share today, and these are the collaborator. Just really want to credit them. They're awesome. Yeah.
Yeah, like Chingy, I can't tell how much I'm exploding with ideas and thoughts right now. Like to your slide 58, when you were
Sure.
explaining. Uh,
Yes. This one.
so
Yeah.
yeah, actually, like I attended NeurIPS this year, and I saw people are using Clip for guiding the strokes and like having larger stroke, smaller stroke, and creating a painting guided by Clip. And
Yeah.
I could like forming some correlations there. And
Yes. Yes.
I was imagining like if in language models they are doing masking and then doing like auto generative, like the
Right.
whole essay based on one
Right.
prompt or starting. And this could even be helpful in construction sequencing. Like you
Yes.
start with the foundation and this can complete the whole uh,
Yeah. 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 Totally. First of all, I think I also agree, like that clip is going to be a very interesting tool for us to explore different opportunities. Secondly, construction sequence or modeling sequence, design sequence in general are like super interesting, and but again, there's not much data about it. So this fusion gallery data set is like one of, I think, if I understand correctly, probably the only one currently in the research field that people have this sequential operation for building a 3D geometry. But of course, if that's possible, for example, like how can we get all the dynamo and grasshopper graphs, or how can we record the modeling sequence from other softwares, and how can we getting more and more this kind of data, such that we can do research on. So yeah, that would be super super cool. And
yeah,
language model in this case definitely will play an important role.
yeah. I'm just wondering like if there are like multimodal models where it it creates like a base and I can say okay, add one more vertical element and the language is guiding the sequence and geometry operations, but
Yeah, yeah,
also
yeah,
and modify, move, like those kind of uh,
yeah, yeah,
operations.
yeah, yeah. I don't know if you are following some of the latest works. There are several papers on Twitter you can find. I guess they are basically using clip to create or generate 3D shapes. Some of them I can paste the link later, but some of them are. Sorry, I forgot the universities they did that, but definitely using clip in the creative field is really popular right now. Yeah,
Yeah, and there was one slide, I think 54, where you mentioned like three very interesting directions.
yeah,
And uh, for your last point, can you elaborate like on that, like how one could do from text to 3D, what kind of data set, like some thoughts on those. And I have seen like people, a rise of like GPT-3 and transformer architecture, like what are the opportunities for us in this space?
yeah, totally. So there are many ways you can think about it. So first of all, if you put everything into language model, that will be okay. And then there are also other ways people are utilizing clips, right? So the papers, one of the paper they recently even released a demo that you can actually say, oh, I want to change the color of this car, or I want to let the car look like this another car or something like that. So I forgot the paper name, sorry, but they are using clip. So clip, you if you know, there's a text encoder and the image encoder, right? So they will basically bringing those embeddings to the same space as close as possible. So that's why you don't really need a language model for outputting, yeah, a representation. Your representation can be a different representation for your output, but you use the language encoder in clip to kind of encode what you want to input. Other things such as, for example, you can also tailor clip or the pure language model to a more domain specific tasks, right? So for example, architectural design. Um, yeah, but what we will be interested in are, of course, all sorts of these things. And we have been working on some of the things, but we will release the result probably early next week. Can't talk about too much right now, but I will definitely keep you updated. Yeah.
I am, I really look forward to what you guys are cooking. And on the reinforcement learning side, uh, I was just wondering, like, ultimately, if you don't take the advantage of reinforcement learning in true sense, it's acting basically as an optimizer, and you could have like genetic optimizer to do similar tasks,
Mhm.
reinforcement learning. And I'm yet to like think about like AlphaGo level or like such kind of design space explorer using reinforcement learning, where the model knows what are the possible design outputs for each design step sequencing, and how can we like make guide the user not towards the design but also better performance design.
Yeah, that's definitely interesting, but there are several concerns. Like generally, RL agents are much harder to train, and also design space is like super big for, just if you only look at architecture design, it's already super big. So what I'm more interested in here is that not to let agent to solve everything for us, but instead it's more like building a multi-agent system where the designer is also an agent, and then you have another agent. You guys are actually working together, right? So in that case, none of the agent will need to know everything or be able to solve everything, right? So it's similar to this setup. We are actually still not allowing the blue dot to handle everything. We are still allowing the green dot, which is the human designer, to drive some of the things, right? So similarly, if we have IRO agent, we just have the same environment, like different players, and then how they can work with each other. That's actually a more interesting direction I would be looking for. But of course, eventually, if we can have very strong IRO agent that produce very new and seeing results that still fulfill all the design requirements, that will be great. But I personally less interested in those directions. I want to utilize the nature of IO system more like a sandbox people can interact. So that's my interest. But the other direction, of course, is cool. Yeah.
I see. And can you briefly describe your work in semantic representations and detailed flow plan?
Yeah. So semantic representation is just a high level word. So if you think about the output from house scan or even from building scan, those are not really floor plans with real floor plan lines or drawings or even furnitures or details. Those are just like room arrangements or volume arrangements, right? But those are still important representation for us to design or explore early stage ideas. So detailed one is more like when you want to finalize or input more details, and of course there are there will be interacting between these representations as well. But the high level idea for now, at least for building GAN and house GAN, are producing the semantic level representation, not the detailed floor plans. But of course, we are willing to explore that as well. But data set is
Yeah,
the biggest issue, right? So there are not much we can do over there yet. Yeah.
I see. And one of the area I was looking into, but I couldn't like find much information was
Mm-hmm.
uh like we had a time where a lot of people were experimenting with style GAN and producing like building floor plans, render, and
Yep.
all those was in the raster image format and
Yep.
image space. And if I want to translate that into vector format of lines and edges, like I couldn't find like a good algorithm which could do that conversion or like that translation. Curious to know if your thoughts on that. Like,
Yeah. So if you remember my first project, it's exactly in doing that kind of thing, right? And that's also why we had this project, right? So we want to be able to look at one floor plan image and try to draw that vector drawing. But there are some existing works, like from Simon Fraser University, Professor Furukawa lab. So they have some work about converting image drawing from floor plan to vectors. Um, there are also many people who are doing wireframe generation given a natural image. And also the SIGGRAPH paper I mentioned earlier this year is also trying to vectorize any line sketches. Those are all, I think, relevant works that potentially can solve your problem. But I think fundamentally, that's also why I changed the representation for building game. Fundamentally, is like we want to directly produce those representation instead of doing a post processing, finding another network to convert it, right?
correct.
So yeah, that's what I'm thinking right now. But still, there are lots of related work or models that are doing similar things. Yeah,
I see. And like I have like few informal, non-technical questions for to
sure.
wrap up the interview. So
Yeah,
first is there is so much research going on in AI. There are so many developments. How do you keep up to date?
I can't. So, so the short answer is I can't. So the longer answer is like I when I started, um, I really try to read as many papers as possible every day. Also, I made many like very long Google spreadsheets that are tracking all the papers and I have been reading and why they are relevant and everything like that. But and also I was organizing lots of reading groups or paper sharing session internally at Autodesk. And to some point I found it's just impossible to cover every single field. So in the end, what I have been doing recently is more like whenever there's a conference such as CVPR or NeurIPS, and whenever I saw something interesting on Twitter and I think that's relevant, I will basically spend my time to pick some of them to read. For example, whenever I attend a conference like 1,000 paper, I will basically walk through all the posters one by one and then mark the relevant ones, seemingly relevant ones. And then I will always have a very big deck, like several hundreds of them, right? And then whenever I have time, I will, or whenever I found something relevant, I want to look for answers or relevant works, I dive into those decks. But I'm not expecting I can read all of them anymore. So that's a reality, right? Just too many paper, like 1,000 per conference, and then although not all of them are relevant, but at least for every conference, you can find at least like 20 papers that are super relevant. And every day you can also see that there are cool works tweeting on Twitter. And then there are also many interesting subfields right now, like neural rendering, clip, language modeling for other type of image or 3D related tasks, and then all the 3D related work, how we do modeling, how we do reconstruction, how we do design. If you want to track everything, this is impossible. So first of all, and you try to collect as much any paper or as much information as possible and try to keep your information updated every day. But don't expect you can have time to read everything. Eventually, you need to pick the relevant papers you really care about, or the when you are starting a project, you will also, based on that project, what are the closest relevant paper or works, right? So yeah, that's what I feel now. I don't feel confident to say I'm updated every day anymore. But I'm more confident to say that although I will definitely miss some paper every day, but I'm not too worried about it, because as long as I start a relevant topic, I will be able to reach to those papers, right? So yeah, don't be too panic. I think, yeah.
I see. And I'm curious to know, like, how does it like working in Autodesk AI group looks like? Like, there are also many other AI researchers in the group, and how does a day in your life look like?
Yeah, it's pretty flexible. So the research organization is in those tech companies, not just Autodesk, are not like product teams. They have very strict cycle to deliver the new version of software and so on. So in research, it's more like how you can come up with your own research topics, and that topic has to align with the high level directions of Autodesk vision. And also, oh, what happened?
Oh, no, like the screen. Yeah,
Yeah, okay,
yeah.
got it. So yeah, so basically, the day-to-day life is when you want to propose a project, you want to make sure your project proposal is aligned with the high-level direction of research or even product, and then you also are flexible to collaborate across Autodesk internally. So in Autodesk Research, we have not only AI lab, we have a robotic lab, we have HCI research lab, we have simulation optimization research lab, and so on. So, and we also even have like specific industrial application related groups. So for example, AEC or manufacturing. So you are allowed to collaborate or formulate project with anybody. And even like you can see, many of my works are actually collaborating externally with academia. So you are also allowed to do so. You also need to kind of engage with customers and product teams so that you will be updated, understanding their goals and their plans. and and yeah, I think those are kind of the daily things we will be working on. But pretty much I would say very similar to grad school. For example, especially like in a professor's lab or as a PhD student, but just a little bit more responsibility to understand or to align with the business purpose. Yeah.
Got it. And based on your experience, what were the challenges you faced when you were learning about AI in either in the research papers or implementation, and your piece of advice to young professionals who want to do similar work?
Yeah. I think it's really trying to uh, the understand the spectrum and understand where you want yourself to be at this spectrum, right? So for me, as I said at the beginning, I only want to do apply, right? So I was not too worried about if I can produce algorithm or not. I just a little bit uh, spend a little bit more time understanding the implementation, trying to do that, and then so on and so forth. But later on, when I try to dive into the algorithms, and I definitely found, okay, now I need to read 100 paper per month, and is that even possible? When I read the first paper, I don't even understand what does that mean, right? And then I found in order to understand this paper, I have to read another 20 paper to understand these papers. All these kind of things are really difficult, but that's how you learn, and that's how you build your strengths. But also that's basically by your own decision, right? So if you are not really into that, why do you need to read 100 paper a month, right? But if you do want to do that, 100 paper a month is not even enough, right? So it's really about your decision. The the difficulty always, I think, is to decide, right? So to have a stopping point on all the interested areas, right?
Yeah.
I mean, every area is like super fun, super interesting. No matter it's in AI or actually in design, those are super cool, super fun. But when do do you make a decision that, okay, this is the boundary I'm building? I think that's the toughest thing. And secondly, I also remember when I was at MIT taking all these courses, I was like, oh my god, I forgot all the math, and I had to pick up all the math. I mean, it was actually a little bit easier for me because I studied engineering school, right? So that was, but they're just like too long ago. I have to spend a lot of time. So I remember the first class I was taking at MIT, I dropped it because I like before the midterm I found, okay, no, I actually not yet, not ready for it. So that was like, I remember like the first or second semester at MIT, but I dropped it. So after another half year or so, that's how I resumed that class. So basically, you know, it's difficult also when you are in a competitive environment, that like how can you get a or even just B with all the super smart uh, computer science major students, right? So it's like almost impossible, I felt. But it's also your own decision. Once you decide to do that, you will find some way to at least make it okay, right? So for example, what I did is like for AI course, I remember what I did is like I watch all the course videos uh, before every class. I I try to understand everything even before I attend the class. even including the joke the professor made. So in this way, I gain more confidence, right? So when I was in class, I feel okay, I'm following everything, and that build up your mental strengths and also make you more comfortable when you can even interact with the professor of their from their jokes. You feel like, oh, okay, I'm part of the class. And this is like how I did it. So not just reading, watching the video, but also did a lot of reading before the class, and luckily many of the classes like are has recordings online recently, right? So nowadays you can easily find any classes in Stanford, MIT, and so on. So you can do a lot of work you by yourself, and then to gain this kind of confidence. But this is a long process, but as long as you want to do it, I think anybody can do that. But and also another thing is like, even before 10 years ago, like I found for architectural designers, it's really not that hard for them to learn coding if they really want. The most important thing is if they want or not. Because I think the training of architectural design or even civil engineering provides you this ability to think in a logical way, and to actually even think in a graphical way, in visual way, and that really helps to understand algorithm, to code, and when you have a purpose and then you really know what to do, and learning coding is not that hard anymore. So I remember when I was in engineering school and mechanical engineering, I took the first semester I had to take like C++ class, but I forget everything like right after the class because I have nothing to do with it, right? So it is not relevant to any other things that I'm taking the classes and so on. But in architecture school, like I found, oh, everything is relevant. Like I can do anything whenever I want to achieve something. I can imagine, okay, if I can do this by coding in this way and so on, I can potentially do that. So finding a purpose and then having this design training, I think is so relevant to learn coding and even AI. So yeah, just don't be afraid of those mathematical things, and try to make your own decision, and try to dive into those. I think that would be it. Yeah.
I think like that's a great piece of advice, and I could literally feel that when time sometimes you're taking those AI courses, like you have those self-doubt moments that okay,
Yes.
everyone is getting it, like
Yeah.
what am I doing wrong and stuff like that.
Yeah.
But definitely that mental confidence,
Yeah.
it really helps. So I definitely
Yeah.
recommend that. And
Yeah.
also like because of grasshopper, and like we are already thinking algorithmically, and it's getting better and better.
Yeah.
And for people who wants to get into AI, I think like at this point it's uh, there's so many free resources on courses on
Exactly.
YouTube or Coursera.
Exactly.
And
Yeah.
also if you find some interesting creative AI paper, they also have collab scripts, so you could just go to the collab, understand the
Right.
code, and just play it. So like curiosity driven exploration, I think like goes a long way.
Yes. Yes. Exactly. Totally.
Yeah, I think it's almost 2 hours, and I lost track of time. But I have like two questions before we end the
Sure.
interview. So, what is one technical or non-technical book which made a big impact in your life?
Huh. Interesting. Um. I mean, so a book might be a little bit too formal. Can I
Or
jump into
video or
something
movie?
informal?
Yeah, yeah,
Yes. Yes. I I was a big fan of animation when I was even very young. There was a there are actually, maybe just use one. So there's a one animation. This is basically it's called Cyber Formula. Basically a racing car, anime, and it's basically talking about in the future. Oh, actually, it's not in the future anymore because it was 1990. The animation is 1990. They are talking about like 2015 or 2016, like, but we are already passing that. Yeah, but anyway, they are saying like in that world, F1 is not any F1 anymore. It's like people are driving a more intelligent car that can be basically faster and do a lot of cool things. And then one of the episode is like they had a company. They are building a very strong a car with a very strong AI that can directly manipulate the driver. So so the driver is just basically sitting there being controlled by the algorithm, by the AI computer, and the other side is like the main character. He was driving a car that has also an AI system, but that AI system is very rude and very have a very interesting personality, and that tries to always to fight with this driver. And then eventually they learn how to work with each other, and then they won the race, uh, win over the controlled one, right? So that's actually, yeah, that you know really, when many years later, when I started to think about AI and when I think about how we can build an interactive design system, I thought about that animation, and I think that's the answer, right? So for me, how we can work closely and interactively with algorithms, with tools, and how we can preserve our own creativity, how we can drive the design ourselves is actually the goal for me to explore AI, instead of having a strong AI that eventually control or compute or construct everything, right? So yeah, I think that's the thing. If anyone asks me the philosophy or the inspiration, I will always talking about that. Yeah, I hope that makes
Uh,
sense.
yeah. Like I will check that anime out. But
Yeah.
uh, lastly, in one line, what is a message or a thing which we didn't cover in this interview, but you'd like to share?
Okay. Let me think. Yeah. So um, having a strong goal or destination of your career is good, but trying to explore or jumping around is also fun. So it really depends on your personality, right? I'm the later, but the former is also good. So it's trying. Oh, I mean, as I said many times in this call, I think the most important thing is to understand yourself and make the decision, right? So yeah.
Awesome. Thanks a lot, Chingy. I learned many things in this interview, and your work is very incredible, pushing the boundary in AEC AI research. And thanks a lot for your time for this interview and sharing your
Yeah,
thoughts with us.
thank you very much for inviting me. I hope we can keep in touch, and I also welcome any audience of this interview to reach out to me if they are interested in know more about the project details, or have some interesting thoughts we can exchange. Yeah.
Awesome. I'll share
Awesome.
your Twitter and LinkedIn information in the video description for anyone to reach out.
Okay.
Have a nice
Awesome.
rest of
Thank
your
you.
day. Bye bye.
You too. Happy holidays. Bye.